talk about the streamers.
Okay, let me introduce myself.
Yeah.
Thank you all for taking time off to spend this afternoon with us. And it's a Saturday, I understand. So thank you very much. I'd like to thank Michael Borresen from Audit Group Denmark, Chief Technology Officer, and he's the one responsible for this great music for you guys. So pass it over to you, Michael.
Pass it over to me.
To me, to you. To
yeah, I've had a very privileged life. I have never, that's not entirely true, but in the last 20 years, I never felt I had a job. I always just do things I would like to have myself, basically. So that's the philosophy driving. Lars and I met in 1987. I started studying engineering in Aalborg, and Lars had a hi-fi shop there. And every Friday he would host people like you, or I was at that time. I came to see him because he has free beers. So on the way down back home from university floor club, Friday afternoon, and a talk with Lars and a beer. That was nice. But hi-fi has always been in my blood. Making speakers has always been in my blood. I was very fortunate to live in a house where there was big freedom, and every time I said to my father I would like to have, he said, "Can't you make it?" So speakers became sort of my weekly project, because 7th or 8th grade, a Speakz factory burned, and my father and a colleague of his, they bought from the insurance company all the drivers that were not damaged in the fire. So I always had drivers. And my father, that was a teacher, but he also had a wood workshop, so I could make cabinets there. So I cannot count how many, every week a new speaker project. But I learned how things work. And then later when I started university, I built speakers, these big duetter types, foil dipole speakers with big huge membranes. I built a lot of those. So made turntables, made a lot of things. Also as part of my education at the university, I was supposed to do something that involved a bearing or something like that. And I thought that, okay, we need a bearing, so I make an air bearing for a turntable. So we need a gearbox, so I made a gearbox with a pulley and a big diameter, so I have a gear ratio at least. So I made it possible to make that kind of projects in university. So I always sort of had this as my niche. And up through the 90s, I was working, I had a real job, making airport trolleys. So if you go through Schiphol and get the trolley there, I probably designed that one. But anyway, during that time, I made a tweeter. And my idea was to make a very, very good ribbon tweeter and then sell the rights to production to Speakz so they could sell it, because I knew I could make a better tweeter. But Lars Scholler there did not like it because it was too quiet. Even if it measured loud, it was still too quiet. It did not go, just made very gentle. So they could not really get them to working with their drivers. So they did not want to pursue that. So I said, okay, I have to make a speaker. And then I by accident ran into Lars. And by 2002, we started Rider together. We started that together with an industrial partner. So Lars could do the sale, I could do the products, and then we had the industrial partner could keep up with the money. And then we continued that journey until the financial crisis. And I had a spare job, made money outside the business, and Lars had his job for Nordost. I worked a little for Nordost, but eventually we could start to take out a little bit of salary, and then the financial crisis hit, and our financial partner had to pull out and sell their shares, and Dantak said, okay, we will buy your shares, but we will also put in a little bit extra money. So Lars and I was voted out. Instead of having majority, we became a minority, and that created a conflict further down the line. But in the meantime, we had started the cable project, the Ansuz, and we also started the Aavik. Also, Dantax has been business partners there. But these two companies we started, so Lars and I had the majority. They could have 1/3. We each brought the same amount of money, and then we started the company. And then we did. All of a sudden, we could not anymore see ourselves in a situation with Rido, because John Jensen, who has been in loudspeaker business for more than 3 decades, all of a sudden wanted to be a part of the design team and make crossovers and make measurement rooms, and everything had to be done in a totally different way. And then Lars and I left, and that was maybe 8 years ago we left. And then we ran into all kinds of financial things, because all of a sudden we had a company. Together with the company we left, and we did not like the owner. There was a lot of things, so we had to try to maneuver it and make enough money inside our company to have enough capital to buy them out. So we ended up that our company simply bought the shares from Dantax, and Lars and I owned everything. And then when we owned everything, we started making speakers again. And that was, I think, 5-6 years ago we put speakers out. So we were out 2 to 3 years of that Rido Dantax ownership. And when we started making speakers, we sort of had, and we owned everything. Then we had this group connected, so we could make Audio Group Denmark. We have now also a fourth brand called Access, which is more of, it is not specialized. Børresen is speakers, this is amplifiers, electronics, this is cable and accessories, the Access. So those companies are high-end specialist companies. Access is more broad and can actually have everything: cables, switches, main boxes, amplifiers, speakers, everything, but at a more less specialized price point. It is so that when you do something really high-end, all of a sudden you have this idea, you see this mechanism work really, really well, but it's not really an expensive one. That goes to Access. So Access is sort of like a fruit of all we have been doing here to bring good quality performance, high performance to more people than we are capable of doing here, because what we do here is, frankly, quite expensive. So I think now we can play music.
Yeah. So Michael, thank you for the short introduction.
That became a little long.
Okay, so we have 3 different setups in this venue. We have the flagship setup, which is M series, and the I-880 series. Then over there we have the new U-588 Unity M, and the C3 and the T1. T1 speaker is a world premiere, first time shown in the world. The T1 bookshelf is something else. After this, you guys can pop over and have a listen.
All the music, and the fact they did that is, when we play old recordings, is the reason we have them still. So if they had not done that, there would not be much Beatles left. There would not, because age simply takes away the quality of tapes. Even if you store them correctly, they lose their power. And vinyl, you know, scratches. So we could simply not have the music library we have today if it was not put into digital. Now all the audiophiles at that day, they hated it. Some still hate digital. And it's not really the digital formats that's a problem, because putting analog into digital is sort of like an observation process. It says at this time you have this level, or we store that. At that time you have that level. There's nothing physical in observing something. But the other way around, there's a physical process where you have a data, which is basically a numerical value and a time, and that you have to convert into something electrical. And that process is discrete, and it's a physical one. And in every physical process, there's reaction and there's action and reaction. There's sort of like they push towards each other. They don't want to change, but they have to change. So by adding at this time this value, you basically the original way do that in a ladder type DAC where you have 16 switches, 16 resistor values, and then you open from the number that, and then 1/44,000 second later you open this, and then you open this, and maybe those samples are too far apart, then you oversample, and then you open this, and so basically you have this process, but this process is always, a switching process is always, has you put a signal to a switch and say, now you open, and he says, yeah, I will open, but I need a little current first. So it's always a little timing thing. There's a little delay, but there's also this, when you open something, you don't open and just have a signal that's perfect. You have a signal that's overshooting a little bit, so you have small ripples created every time you play a sample. And that ripple is noise, and I believe that's why people hated digital, because it came out pointing at you. It was aggressive and pointing at you. It played from the top down, rather than if you put on the same track on a turntable where the bass is sort of preceding the whole thing and every energy comes out at the right timing. I think that was what we were facing. Later on, what was his name? Playback design, Andreas Koch made the DSD, and then he changed sort of like the way we do digital to analog conversion. Because that modulation, he did that on top of the Super Audio CD made by Sony, and then he further developed that into DSD, which was simply a work on top of what Sony already did with the Super Audio CD. But that's sort of like the background for creating what we did here. When we started Aavik company 10 years ago, maybe, something like that, I think, we first made an integrated amplifier, and then we made a preamp, and in that preamp we actually had two DACs. We had one for DSD, and we had a DAC for PCM. So we had a typical ladder DAC, and then we had a DAC that could do the DSD, because that was in demand, now less in demand, but still out there a little bit. But that DSD DAC, because DSD has the modulated form, has the analog signal in, so that was just, we did a DSD DAC the way you do a loudspeaker. So you take the DSD and you amplify the DSD, and then you analog filter it. So we made a filter like I would do to a loudspeaker into a fixed impedance, cutting off at 50 kilohertz, fourth order, sixth order, whatever was needed at that time to create an analog signal. And that had some qualities that we did not have in the PCM ladder DAC we used for normal PCM coming out of a CD player. That had some qualities, but it did not have, it was not really fully clear, because I think that these components, these coils and iron bits and capacitors all added a little bit to the proceedings. So putting a loudspeaker filter into electronics is maybe not so good idea, but it worked, and that created the foundation for what we have here. So the streamer module here can accept almost any format out there, being DSD, being 32 bits, 300 something kilohertz sampling. We can tune that, and then we do a conversion into a 2 megahertz, a 22 megahertz DSD type signal. Take the I2 square and convert that into 22 megahertz, which is roughly the same sampling frequency as DSD 512. So you have so many samples. Yeah, DAC sample, please. It's nice. So we have them in one box, because if we would take the I2 square and try to take it outside and into a separate DAC, you need a conversion from the I2 square into USB, because, or HDMI, which are the only cable between the only interlinks you can have that can transfer that high data rate. But the chips that you get to convert and reconvert, you need two conversions. They are not very good. They are not made for audio, so they are noisy. They are not very clear. So we didn't want that solution. That's why we put it in one box. And having it in one box also let us clock the signal internally with a very, very high precision clock. And then we have this 22.6 megahertz sampling rate. And then after that we have this. What we do is we take 32 of those samples and take the sum of that, take the average of that. We take the sum, actually, that it becomes an average because but when we take the sum, the value is higher. So the signal to noise ratio is highest when we take the sum. We don't need to divide and make the signal smaller. So we take the sum. That means that every time you get a new sample, you get a new sum. So 22 million times a second, we get a new sum. So we have this signal coming out of that summation circuit, being an analog, but following all these samples. But because we have 32 of them, that means if one is wrong, it only influences 1/32th part of the signal. So it gets very robust that way and reduces simply noise spikes that could end up for some reason. When you do digital stuff, there can be noise spikes. So we have this summation circuit. So we upsample to 22.6 megahertz. We take an average or sum of 32 of these samples and have that as a continuum moving. And then we have a discrete op amp and a first order filter at 100 kilohertz. And that's basically it. It's a very different approach. I know there are some that are a little bit similar. Lampsinator DACs also do this upscale to DSD, high DSD 256 I think they go to, and I know PS Audio also upscale to DSD audio in their DACs. I think they are also to 256 or maybe only 128. So but we go to 512, which is the highest resolution DSD you can go to. DSD type, it's not really DSD, but it's similar. And I think that we have moved into something that plays much more like a turntable with the energy coming from below rather than from the top. And I think that for me there's no doubt that the two formats I love, I use is streaming because it's convenient. I have at my Tidal Direct or Cubus or whatever streaming platform I use, I have access to everything. I can make playlists, I can make something for a nice dinner, I can make something for my friends for party, I can make, and it's nice, it's easy, it's convenient, but sometimes I prefer gourmet food, and then I put on my turntable and I play an old album, and I know exactly when that scratch in that track, what happened that day. It's a funny thing, it's like a memory bank you pull out. So I think that the analog and turntable will live alongside of this, and I see this as an ideal scenario for music going forward. Amen.
Okay, thank you, Michael. So, any question regarding this streamer deck on the floor?
Maybe one question.
Yeah.
How much emphasis from the designer point of view for a streamer is the linear power supply? Do you use external linear power supply?
No, we don't use linear power supplies. We use always resonant mode power supplies. We also do that here, I think, and then we use heavy regulations. I think we have more than 14 or 16 different power supplies in that because this needs this needs that. Linear power supplies are winded with copper, and the transformers are quite big for the power they need. And when you have windings close together, you also have stray elements to that. It's not a pure inductive process. It also has capacitance. And capacitance from one side to another is like a highway for noise. So when you lose a linear power supply, you think you rid yourself of noise, but you actually invite noise in. Resonant power supplies are much quieter because the transformers they need are very small, and the capacitors they need to because they run on a high frequency, the capacitance they need to get a DC out. I mean, on you have a 50 hertz ripple, maybe in hundreds of millivolts you need to straighten out, and you have these corners you need a diode to open and close. You create switching, and you do that at 100 hertz or 200 or 120 hertz because you have a dual bridge. So you create noise. A linear power supply is much more noisy than a resonant mode power supply. And resonant mode power supply are quiet because they run on sines. They're not running on anything that's edgy. They run on sines. And it's the density of the sines, the frequency and the density of the sines that decides how much power you're pulling within limits, of course. So we use resonant power supplies. We use that in every single bit of electronics. And from our point of view, it's also very convenient because you can plug it in here, you can take it to US and plug it in there without any alterations because they are very tolerant of voltages.
So my quick question. On the data, music data that is coming into your streamer.
Yes.
Of course, in the market right now, there are a lot of talk on putting an extra switch where the data coming, go to a switch, normal switch, you go to
The streamer, yeah.
And seems to have a few school of thoughts, and the few school has proven that adding a switch in between does improve the data.
Yeah, the thing is that most of the internet you get is not really, it's floating. So you have a ground that you don't know where it is, and the difference is there. But when you connect to the internet, you also connect to a neighbor, or the whole neighborhood, to the whole city. So all the noise, so it's not only a World Wide Web of data, it's also a World Wide Web of noise. And most of this noise is on the ground side. Because every circuit that receives data is very good. It's not like you send a spreadsheet to China and get it back, it's different. You preserve data really, really well, but the difference is what's associated with the data. How much noise do you actually import into your system? And that's where, like one of our switches, there are other brands that make good switches also, but our switch use technology from, I was once working in the maritime industry where we did GMDSS, Global Marine and Distress Safety Systems. And there when you have a boat, you cannot have the same ground everywhere on a boat. Because if you take the antenna ground on a VHF radio and attach that to ship ground, you get corrosion in the whole ship. So you need to detach the grounds, but you cannot detach the ground at high frequencies. So that technology of putting ground to something that's actually floating is what we use in there. So we create an extra ground. So we try to ground and get these ground noises, these noises on the ground side of your internet out. We cannot get it all out, but we can improve it for sure.
Okay, so just for information, we have also switches by Ansuz, starting from 3,000 onwards, all the way to go for 23,000. So right now I'm using Gold Signature, the top model for the switch. So that's why you get a very quiet streaming. Okay, we will start the next one. The amplifier, this is the I-880 flagship amplifier, and is biased in full class A. So how does it achieve a full class A with such a small body and without much heat sink and so low temperature? I'll let Michael Borresen explain.
Thank you.
Thank you.
You've heard it 3 times, now you can do it.
Yeah,
the thing is that normally for bigger Class A amplifiers you need big heat sinks because Class A is associated with heat, but heat is not really a necessity for Class A. What is needed for Class A is that you never switch. So we need to keep amplifiers out of switching. If you can keep amplifiers out of switching, they are running Class A. They're not running single-ended Class A. No. but they are running push-pull Class A with no devices switching. And why is switching bad? First of all, there's no such thing as a Class AB amplifier. It's a Class B amplifier, and then the first 10 watt is Class A. But then it switches, and when it starts switching, it's hard switching from 10 watts or 20 watts or whatever they put. And if you want to run traditional Class A to 20 watts, you need to pull 80 watts. You need to put 80 watts each channel to have 20 watts Class A, and that pretty quickly becomes quite hot. So if you have traditional amplifiers claiming 200 watt Class A, they are not. Maybe they can run 20 watts, but they are Class B amplifiers with a head start in Class A, and that of course improves things. But every time you reach a transient in the music, you switch. How do we avoid switching? Well, we keep the transistors in a working condition in the output. We use bipolar transistors in the output. And if you can create a situation where the base emitter voltage, emitters attached to the signal go into the speakers, and the basis is what drives the output stage. And if you can keep this voltage 0.6 volts plus the voltage drop over the emitter resistor, maybe 0.7 volts at all time, like you have in the middle the signal, and then you have 0.7 volts and 0.7 volts. If you can create a situation where this does not change, no matter how much current the transistors are feeding to the speaker, then you stay in Class A, and that will just follow the signal all along. But creating this is not an easy task, and if you look at all the old schematics, I think that 95% of amplifiers out there are old Douglas Shelf or Dr. Marshall Lee's designs or adaptations of that. There's nothing new happening in the audio, in the hi-fi business. So if you look doesn't matter. Old Krells, they are same circuit, FM acoustic, same solution, CH precision solution. All of them use well-described circuits because they have been refined over many years, and nobody is thinking about that you could actually do better. But what we do is we put this, we change the situation. So instead of having a normal driver stage with maybe 20 milliamps of current, we have a driver stage run with the lateral MOSFETs, 200 watt output stage driving the output stage. So these lateral MOSFETs, they run at 150 milliamp. And most of this bias spread is not really coming from a resistor. The problem with a resistor is that if you have a DC running down here, maybe 100 milliamp, and you need 0.7, then you need this resistor to be 70 ohm. So we have 70 ohm here, and you have 10 milliamps or 20 milliamps running down there. But when these start conducting, then the current is no longer here to make the spread. They run out there and the spread becomes lower, transistor closes. But what we do, we have 150 milliamps. So if they take 10 milliamp when they are conducting, it's far less of a fraction that we need to maintain higher. When most of this voltage drop is made by the same transistor that's inside the output transistor. So we take a transistor, if you couple it, take the collector to the base, just wire it together to the base, then you have the base emitter. That is a diode. There is a diode in there, and that diode is the same as the diode of the output stage. Well, that means that when current is running here, we have the same voltage drop over that diode in the bias spread as we have out here, and then the little extra we can do with a very small resistor. So when this actually starts to conduct and take some of the current, our biasing goes down, but it never disappears. So we keep the transistor open at all time, and thus it's running in Class A. But it's cold, Class A. The output stage is not heating this up, the driver stage is heating this up. What you say, 45 degrees, roughly. So it goes to 50 when you really push it. So it never gets hot. But it always takes 2 times 60 watt more than what you play into your speakers. Because that's the idle mainly of the bias stage. Input switching here, when you have inputs coming in, everything here is done by LDRs. So we have no physical switch, there's no relays or anything in the signal path. The volume control is inverted topology. So what we do is that when you turn it down, you actually get better data. So you have, when you turn it down, you also turn the noise down. Where normal volume controls, they keep the noise but turn the music signal down. Here we turn everything down, so you maintain the same noise to signal ratio, no matter where we are. We have done this in all our other products as well, so it's nothing new for us, but it's also a place where we are quite different. The physical design of these is made together with Flemming Rasmussen. We hired Flemming Rasmussen for Griffon maybe 4 years ago, I think, something like that, and we worked on this a good year before we were ready to start the production of the boxes and the cases.
So, Michael, I have a question. I understand your Aavik amplifier or anything is all single-ended RCA unbalanced.
Yes.
So, is there a specific reason for that?
Yes.
Yeah.
Yeah. It's a choice. I think if you look at all the tube guys making the very nice tube equipment, none of that is balanced. Right. And it makes no sense in hi-fi to introduce professional solutions. Because professional solutions are made not for improving the performance of the band, but they are made to prevent problems. So when you have a mixing desk with a lot of cables coming in, maybe you have a bundle like this with different signals, some coming from the kick drum, from bass, some from the guitar, and some from the singer. Then you want to have that the singer is the only one you hear in this channel, and in that channel you can hear the kick drum, so you can adjust them. But when you have a single-ended and you make a cable bundle like this, they smear into each other. But here in hi-fi you only have one signal at a time. You don't have multiple, and that signal has everything. So for performance reasons, it's much better to avoid the difficulty in running balance, because the difficulty is you cannot really make a good volume control that's balanced. So that means that you have to convert things into single-ended. It's difficult to switch two things, two signal and one ground. It's difficult. Everything becomes twice as difficult to make good quality. The component matching, the plus and minus matching, it becomes very, very tedious and very difficult. So you lose potentially a lot of quality, and then you lose again because in how to make the apparatus, then you lose again. Because if you choose to make a single-ended inside, which is best for performance, and you want balance, then you need to single-ended balance converter out, and then you do the opposite when it comes in. So we could have a single-ended to balance converter here, and send balance signal over there to another single-ended to balance converter, and the cable is not better, but these two TAT circuits or op-amp circuits are definitely not improving things. So very much when we do high-end design, we go for the simplest possible solution. I'd much rather make a very good speaker driver and have to filter it less than to have one that has a lot of resonances. I have to suck out a lot of the resonances. So we here also in electronics, the simple solutions are the best. The power supply in here, we have 4 power supplies in here. They are all resonant mode. They are from a Japanese manufacturer called Kosu. And each of them deliver 600 watts, so we have 4 times 600 watt capability. So all you can pull out of the wall socket, we can deliver out to the speakers. We have no limitation at all. So even if the voltage into 8 ohm only says 200 watt in transients, and if the speaker impedance was low enough, we can actually deliver a lot more power.
Will this amplifier play down to 1 ohm?
Yes, it will, but it will be difficult to knock out. What happens if you play that low over extended period of time? There will be monitoring of heat, there will be monitoring of DC offset, there will be monitoring of things. So if you have a speaker that is that low, in impedance. Maybe you get a red light and an amplifier shutting down, but that is normally only in faulty speakers or poor design speakers, I would say, if you go down that road.
Okay, thank you, Michael.
So Michael, that is MS inbuilt DSP.
No. It has an analog crossover. So it has a subwoofer filter, so you can take out high pass if you want to run a pair of speakers that has two inputs. Like here, this has actually separated. So this system we could run with an extra power amp if we wanted that. We have an analog filter. DSP, no way. The problem with DSP and subwoofers is that you add minimum 20 milliseconds of delay and you have absolutely no timing. If you use this filter to run a subwoofer and you can do it without a DSP and a subwoofer, you can get the timing correct.
Excuse me. Aavik started out with Class D amps. You're famous for it. And even until now, only this one is Class A.
No. We have had a C300 preamp and a P300 and an M300, which were Class A. So this here, the first one came out. This nice design that looks like a projector came out maybe 8 years ago, maybe 10 years ago. Came out. That was a Class D with a Pascal module. That is maybe what made us famous. But of course, our mainstream products are all Class D. We still have cooperation with Pascal on the Class D modules. Pascal is started by a friend of mine, an old friend of mine, and we have been in the loop around some of their design things. And where Pascal is very different from any other manufacturer of Class D is they have this UMAC patent, and that's how they shape the carrier that switches. And that UMAC is a sine wave switching, so it's a density sine where the density of the sine wave contains the music, much like a DSD is also a density modulation. So they do that, and because they do that, they have far less noise. And where Pascal is much better than any other Class D is because the noise is so low, they can do with much less filtering in the output. And it's the filtering, even a few, not even a millihenry, maybe 0.01 millihenry, you will feel that the sound stage is matte. You lose that immediate energy. It's a little bit the same as if you take a really, really bad high inductive speaker wire. You also lose this immediately transparency. And this is where the Ice Power came out, say we have a very good amplifier here, but it sounded like flat, nothing happened. It sounded flat. That's because of these microdynamics was eaten away because of the output filter. And if they didn't put the output filter in, you could not watch TV and play music at the same time because it was noisy all around. So this is where Pascal is better than anybody else. But the Class A have always been there.
Do you think good design Class D, which is improving every day now, is able to approach
Yes.
performance of Class A?
I think Class A is still the king. If I didn't believe that, I would not design it. But you see, what is good for efficiency is also good for audio. Because when you get new MOSFETs that have a little less input capacitance on the gates, you can switch faster. And when you can switch faster, you have less dead time. And that time it takes for you to tell the transistor, now you turn on, until it's fully turned on, that triangle is a power loss. So if you can get the dead time down to half, you increase the efficiency to the double. So you maybe go from 92% to 93% efficiency or 94%, but imagine in the world consumption of electricity, how much that means. So all these manufacturers of components, they are researching this field very, very hard, and every year you get a new chipset. Analog here, these transistors, the Toshibas we use, from the 80s. This is the last time you get a good pair of complementary bipolar transistors. They still manufacture them, yes they do, and they're still good. But the advantage here is there's no switching, and there's switching in the other. So you still need more output filtering. But as the output filtering goes down, performance goes up, and all of a sudden we're in a situation where we can no longer hear difference. More music.
Okay.
Michael, how about there's some manufacturer doing class A, D. So class A on that, like what you say, the 10-30 watt, and the rest backed up by class D.
Yeah, I think this is a little bit like Quad did with their current dumping. So they have a class A amplifier controlling the output of something else. Yeah, but the thing is that when you take power, most of the power from the class D, you still have the output filtering. So you still maybe get a little benefit, but you don't get the low output impedance, which translate into a lower damping factor. So you will always, with class D, because they have more inductance, have a lower damping factor, and that's what creates this lack of transparency. When you can get the damping factor and the control up, you allow for the microdynamics in the speaker to come out. So every time you reduce that, then you cannot have that peak transient.
So you're saying you either go class A or class D?
Yeah. I think if you do a hybrid, it becomes more class D than it becomes a class A. But class A, I think still is the king. You know, it's a little bit like driving a Hummer. You know, you still have the power and you can clear everybody off the road because you have the ability to go where nobody else can go. So class A for me is still the king. We can do away with maybe only 5% of the induction in the output here to create stability in very high frequency than you can in a class D, because class D, because of the switching, still needs some filtering. And this is not so much for the sake of you and me or for our speakers, we need the filtering, but because every product must be able to pass ESD. We need to have electrostatic discharge immunity, and we cannot surpass the radiated emission, not on the aerial borne and not even on the cable borne. So when we have a speaker attached to speaker wires going from a class D module where we have switching just behind the coil, then it's very easy to get noise out there. And if we take the coil away, we surely will have noise out there, and we cannot go send this sell this to any client anywhere. So that is sort of a limitation of the class D, is that we need to make sure that we are within the CE technical requirements for noise, radiated and cable carried emissions.
Okay, Michael, one last question before we go to the music. I understand the dynamics coming out from these speakers, the transient is, the control is so good. It's because of the damping factor of this amplifier.
Yeah.
So
when you have something that's not switching, and when you have a circuit that is really high in stability, you can add only a little bit of inductance. Then you can get almost the full damping factor out here. And in here we have 8 pair of output transistors, and they are each 0.22 ohm emitter resistance. So you can take 0.22, divide that by 8, and then you can take 8 ohm for a speaker and divide that by that. But then you have to also, this figure, you also have to divide by the amplification factor of the feedback because the feedback is already correcting this. So you have to multiply that by 90 dB. And in total, if you take the speaker impedance divided by the output impedance, you get roughly 8,000 here.
8,000 damping factor.
So it's very high damping factor. Yeah.
Okay, thank you. So we go to the music. The M3 is top of the line, money, no object, all the good things are here. I'll let Michael Borresen elaborate further.
Yeah. When we left the cooperation with Dantax,
Right.
we didn't want to make speakers. So I said to Lars, we're not going to make speakers until we have that idea that can really carry all the way. We need to have something unique nobody else can have, and we always try to work together with the magnet system to create more ventilation, more flux, less influence of iron, and it was not really possible for me to do until one day I got this idea of, instead of conducting iron, if you take this magnet system, it's a very traditional magnet system with an iron butt plate that goes into a T-yoke, and then you have the voice coil, and then you have a top ring, also a pole ring on top, in iron, and that conducts the flux from the North Pole on top to the South Pole on the south through a very narrow gap, and thus increasing the flux there. Iron conducts flux maybe 10,000 times better than air, so it will concentrate the flux right where the voice coil is, where you need the power. The disadvantage of this is that iron is not very linear in terms of flux, and the voice coil itself is a small electromagnet, so you have a permanent magnet creating a magnetic field, and then you have a voice coil trying to blend in with that, and that voice coil magnetism can easily relax the magnetism, so you can easily get less flux in the gap, but it's very hard to push it up where the iron is close to saturation. So the loading and unloading is a very uneven curve. It's a hysteresis curve, and that is very unlinear. That, as a de facto thing, means that when the driver is moving out, it sounds different than when it's moving in, because it looks into different flux scenarios. And the more the transient is, the worse this scenario is. So when we tried to make something more efficient, it always ended up sounding worse. And this was a very unfortunate, sort of like a cat chasing the tail. We could do something, but we never get out of this loop. Until I found out that you could actually squeeze the flux, but it requires something different. So here, instead of one magnet, we have 4 magnets out of neodymium. And I think the one reason this has not been done before is because neodymium is fairly recent and it's costly. So if you have a normal loudspeaker industry all of a sudden starting to use the highest quality, the neodymium N52s, in high temperature variants, it becomes pretty quickly quite expensive to make a magnet system. But this magnet system has so many advantages, it's unbelievable. One advantage is, of course, it's fully symmetric, so you don't have a problem with something bleeding in or not bleeding in. Second, it cannot bleed in because this copper ring has almost 0 impedance, so it will simply try to block the voice coil from having any electromagnet. It's so efficient in blocking that another measure for the electromagnetism is the inductance of the voice coil. And free air inductance is maybe 0.5 millihenry. Put it in here at 0.05, so it takes 90% of the flux modulation from the voice coil away from the driver. And when you have lower inductance, you have faster rise time. You can handle transients a lot better. But the main benefit is maybe it doesn't spike up where the system has a resonance. So where a normal speaker, closed box, reflex, whatever, have a resonance, maybe impedance go to 80 ohm. And 80 ohm is a lot of phase shift. There's a lot of high impedance where the amplifier cannot deliver current, but where the speaker wants to play by itself, so you lose control. So a lot of these issues with speakers booming in room is because of drivers with high inductance. So when we saw all the benefits of this, and we wrote the patent papers and got a patent, then we were ready to start making drivers and creating speakers. So this is sort of like, we have a copper type, but this one, these rings, are made from pure silver, and it cannot just be 7 nines or whatever it's called. It has to be completely pure silver, and the reason for that is that the sterling silver is not pure enough to have any better conduction than this. You will get exactly the same, but when it's pure silver, you have roughly 8 to 10% better conductivity, and also that means you have 6 to 8% lower inductance again. So it's a clear benefit. In here we have 0.5 pound of copper And in there we have half a pound and 1 pound and 2 pounds of silver in each speaker. Not for anybody to look at, but for driver performance. Yeah. And in a way you can say the M is, all the speakers we have now is basically second generation from where we started. Even the L in the access range are the second generation, because we have this type of membrane also in the L and the X and the C and in the T also. This membrane, the base material is carbon spread to, and you see it looks like a checkered thing. And if you look closely at a Formula 1 wing, it's also checkered. It's because this material is very stiff in this direction and in that direction, but not very stiff in this direction. And that means that the most thing that creates a tonal thing, a tonal discrepancy from the ideal, is a breakup in the membrane. And the worst of them is a first order breakup. And that is, you have, if you fix this here and say it's fixed, and then you put the voice coil to it, this little distance can start swinging by itself, like a guitar string. Pluck it, you swing it, and it swings. And when stiffness is all the same around all the radii, it's a uniform material, then that same resonance will stand everywhere. But here, when there's maybe 90% difference in stiffness along the fibers and 45 degrees on the fibers, no radii here have the same distance. So the resonance frequency here and here and here and here, all different. That basically eliminates that ring-shaped dumbbell resonance, and it eliminates a lot of noise in the driver. Now, when I started Rido, 2002, 1998, I made the tweeter for Rido, and then the tweeter was the best, and it was always a chase. First we used audio technology drivers, they were way too noisy. Then we made our own ceramic drivers, they were a little bit better. Then we started treating the membranes with diamond and tungsten and a lot of different things we started, but they were always uniform, so we could change it. We could change the nature of that noise coming from the driver, but we could never get it away. Here we really, really get it away. And the tweeter, this tweeter is then the next generation of that tweeter. When we left, I owned the rights for the tweeter for Rido. So when we left, we had to negotiate with Rido, because of course they wanted to keep on using it. So we made an agreement, they could use it, and I could make a redesign and use the same philosophy and idea. But of course, when you have had something that has been going on for 20 years, it's 20-year-old design, you know exactly how to improve and where to improve. So we improved this tweeter a lot. Efficiency is higher, the materials can withstand a lot more heat, so they never burn. I don't think in the time we have been using this tweeter or variations of this tweeter we have ever seen any problems. Not with burnt tweeters anyway. We have seen burnt crossovers, we have seen burnt drivers, but not burnt tweeters. You can send this around. The weight of that moving area is 15 1/1000ths of a gram. The area is 3 times that of a dome tweeter. And because of this really, really low mass, it has nowhere to store energy. And when you cannot store energy, you cannot have resonances. When you don't have any mass, it's very easy to accelerate. So when you don't have to accelerate something like a dome tweeter that weighs, in my opinion, 35 to 50 times too much, I don't think any dome tweeter, being beryllium, being silk, being whatever, can actually transmit or have any nuances above 10 kilohertz. Maybe they extend to 20 when you measure, but they cannot handle transient material above 10 kilohertz. That is, of course, something I say, and maybe some can prove me wrong, but I think I know a little bit about what I talk about. Here, this spread tone material is on a 4 mm thick honeycomb, so it's actually 2 layers of spread tone. When you go to the X and when you go to the L speaker, the membrane is the same. This one is only 3 millimeter. So this is a stiffer membrane than we use in those. It becomes gradually more and more difficult as you go up. We have not yet been successfully producing with 5 mm. We can make every third or every fifth count, but 5 mm is very difficult because you need to press them down so you have room for the surround and everything here. So you need to squeeze that, and when it doesn't squeeze but folds, then you cannot have a membrane. You can see here this edge needs to be perfect. So this one then has a skin, a little bit also treated. This is a 4/100th millimeter titanium, and all of this frontal area weighs 0.3 grams. So this skin here weighs about the same as a dome tweeter. Yeah. This.
Sorry, I have a question. I said that tweeters which you create with 1.5 kilohertz to maybe 20 kilohertz. With the new technology right now, we have like the reagents, they are able to push up maybe 30 kilohertz, 30 kilohertz, and
Yeah.
above maybe even 50. How does these areas also?
I think that beryllium is one of the better materials for tweeters, but you will still have the voice coil and the edge suspension creating resonances. And beryllium is really, really good because it can maintain almost the same shape, and if it starts to break off, it has very high internal damping. So beryllium is good, but if you coat beryllium with the DLC diamond-like carbon or some of the other PVDs, it gets even better. I don't like the beryllium from Focal. I think it's too bright and too in your face. Maybe also how they make the speakers, I don't know. But beryllium is for sure the best material for domes. But the main problem is that it's toxic. It's not toxic for you, but in production it's toxic. How I control what?
The airiness.
Uh,
Airiness of the tweeter.
I don't need to control that, it's just there. I think that it's narrow, so it has good dispersion. So no matter where you sit in the frontal row, you don't really feel the speakers. I think that every time you have a speaker, that you hear where the speaker is because it generates some kind of noise. That could be a suction out in the frequency band. That could be that you have resonances that are different at 90 dB and 95. If you have different resonances, you hear something flickering and not stable. And I think every time you have that, it's for me a warning sign something is wrong. And I hear that all the time with dome tweeters because they have this, especially silk domes and textile domes, they have this all the time. It's that is noise generated by the driver. And for me, it's a clear must in making speakers is that we take ourselves out. We cannot have a speaker that does something to the sound. Our job is to make Dean Martin alive. And we cannot do that by making Dean Martin with something extra alive. So our job is to take ourselves out of the equation if we can.
Michael, he was asking what's the frequency range that the tweeter can?
Yeah, well, we cannot measure any further than 20 kilohertz. But in the old days, I had a Borresen Care equipment, and I could see this go way beyond 50 kilohertz, the old tweeter. So I think this will do the same because the membrane is lighter and the magnet system is so it extends way beyond. Actually, I was approached by the US military one time asking me to supply them with drivers because they wanted to see if they could make something very high frequency modulated in a way that it annoyed people. So the driver, but the problem with the old tweeter was it could not handle the power. So when you try to make it go really, really loud, like 115, 120 dB, it could burn all of a sudden. But this foil that is now being sent round, the carrier is called PEN, and that PEN foil actually exceeds the aluminium traces in heat resilience. So this one cannot burn until the aluminium melts. And if you see here, there's sort of like a grit here in front. It's very near the membrane and also on the back side. And that is made from copper. So that is also a heat sink. So we put a heat sink on the front and the back side of the driver. This copper also acts to stabilize the flux. So the magnetism from the coil, because it is a coil, around does not affect the working condition because we have all this copper around. I will send this around also, you can have a look, and then I think that somebody will play some more music.
Okay.
You can ask questions.
You guys can ask questions. Then I will play 2 more tracks, and then we can call it good evening.
Okay, Michael. As a speaker designer, how much of your emphasis is on the speaker placement? I don't think we can deny that different placement you get different sound.
If you look at this, we have been fighting a little over that. Kenny got to decide in the end.
Yeah.
That's okay. It's his show. I will place the speakers a little bit different than here. But when you have a long room like this, I think it's very important to get the speakers out. These are very robust from the side. So if you have a smaller room, they can be closer to the rear wall, but they need to go out wide. And this is what I would have changed here. I would like to have the speakers wider because it creates a bigger space. And because the reflections are so homogeneous that if you just have a plant like this to break up the first, then you don't hear the side walls. You just create this humongous space in between the speakers. So I think, of course, speaker placement is very important. And one room has not only one placement, but there are placements that are better than others. And especially in this long room, it's important to get it out, because if you hit something like a quarter distance, then the bouncing will surely happen, some frequency. Maybe 80 hertz, you have some, this is maybe 40 hertz, 50, 60 hertz, you will have something, and that will affect the drivers. They will want to play at that distance. But the more you get away from something that has a fraction, a true fraction, the less the speaker will pick up room notes and room resonances.
Is there a quick installation placement guide?
Yes.
Of like so that the interactions between the drivers, the speakers, and the room can be optimized and less problematic.
Yes.
And how do you overcome this variation? Because a
but the thing is if you go to where the speakers are and you start clapping your hands. Now I have a watch, so my hands hurt when I clap. But then you can hear the flutter, and then you find the place where the flutter is the least. So you walk around yourself around where you want to place the speaker and clap in your hands. You can hear the flutter, the reverb in your room. You can hear that. And when you could get that down to the lowest degree, then you have roughly the placement. You can also do another thing. You can take your speakers and place where you want to sit, and then you take a chair, and then you move around and listen to the speaker. How does it sound where you are sitting? Because if the tonality is good and you don't hear the room, then that is the placement of the speaker. So there are a few ways to do that.
Do you agree with the golden ratio of 1/3?
Yeah.
We have 1/3 here, 1/3 on sitting distance. In relation to the room.
I like the speakers wider than that.
Wider than 1/3.
Yeah. I don't mind almost 90 degrees rather than 60. 1/3 is like 60 degrees. I like them further out. But we can only do that because our speakers are so low in noise. If you do that with most other speakers, especially the ones with dome tweeters, you will start hearing the speakers rather than the music.
Empty in the middle.
Yeah, empty in the middle.
Yeah.
That you will never do with this.
What about toe in? Do you believe?
Yeah, I believe in toe into the shoulders, roughly to the shoulders. So you are sitting in the right place.
Yeah, question around, I think the designs are always 2.5.
Yes,
right?
yes.
Why not more than that?
Because if you place a crossover right where a male has his voice, or the bass, if you place a crossover there, you get a phase shift going over the crossover region. So you can make something that sounds or measures pretty linear, but it does not bring the they sound weak, they sound detached, they sound three-way. I think that I can always, when I go into a room, hear the bass is here, the mid-range is here, the treble is up here. That's because you try to put too many components in the crossover network. Here is essentially a two-way speaker with a subwoofer. That's essentially what it is. These don't play much more than up to 80, maybe 90 hertz. Then they roll off.
Is that
very
also the
gentle.
reason why you have very small drivers? Like
Yeah, I think that one reason here on the M series we have small drivers is because this membrane, when it gets bigger, it's very hard to control the flexing. So when you have a bigger driver, you put a transient through, it flexes. Sometimes we send drivers down to Germany where they have some optical measurements. Then you can see the drivers, how they flutter and break up. And I don't like that because it sucks energy out. So to get this energy punch, I'd rather use more drivers than to get the area if you need the area. But if you take a normal 12-inch driver in a BMW and you look at that, then the area under transient is actually smaller than this. So I don't see the benefit for the added weight and the flexing and what. I don't like that.
Does the footing design or material, the forefoot of your speakers, how much does it affect the performance of the drivers or the speaker?
I think the enclosure affects a lot. A little bit like if you take a Martin guitar, the wood they use is what makes a Martin sound like a Martin, and not like a cheap guitar built in China. I think there's a profound difference in using materials where the sound is something we like. And this is also the reason why we make the basket from zirconium in this speaker, because mind you, when the driver moves out, the membrane, the mass pushes a magnet system in, so you have something that do like this to the basket. And the tone of that basket will always be overlaying what goes on in the speaker. So you want to have something that always, no matter in what situation, create a tone that we like. And it seems like there are certain materials we like, but what we have seen, there is a connection between what we like and what our body actually accepts. So our body accepts stainless steel and titanium because that's used for implants, and it also accepts zirconium. So if you have something stainless steel, most often they will be plated with zirconium because then the tissue can faster grow to it. And I think there is some weird connection that I don't really know how to explain, but we have these devices that we put underneath everything, our darks, and the best ones we have are zirconium, and they sound just much more natural for some reason. I find hard to explain, but I think that's the reason also why we use it. That is the reason we use it in the basket here.
Okay, one last song for the road, and then you guys can enjoy.
I was no more than a boy in the company of strangers, in the quiet of the railway station, running scared.